So first of all, we have introduced something called linear regression, which is really the simplest machine learning tool that you ever have. Then we have learned that it's not as simple and actually is more powerful than you might have thought at the beginning, because you can use generalized linear regression, which is the same thing. And it actually gives you lots of nice functions that you can choose from. And so we seem to have a good, and then we have done some machine learning theory to see how to select good hypothesis spaces for your learning system, right? So we have got a good grip on a regression thing. So basically, when you are trying to estimate a real valued something from a real valued feature vector, right? So now I want to go and switch to a different problem, which is called classification. So this we are still using doing supervised learning. But now it's not regression, now it's classification. And I mean, the question is why it's not the same. What's the difference? The difference is that the target variable, I mean, you still have a feature vector that is most likely real values. And then you have a target variable, and the target variable can be what? It's just, let's see, either plus or minus, right? I don't know, good student, bad student, or I don't know, cat or not cat. Things like that, okay? So instead of real value target values, we have target values. In the simplest possible case, we just have two classes, and we usually call them -1 and +1. Okay? So, is this a cat or it's not a cat, right? This is a cat, this is not a cat. You can also have multiple classes. Usually decomposes to several classification algorithms that actually classify each class independently. Belonging to that class, not belonging to that class. Not always, but most of the time that's true. So in fact, what we will do, we will exclusively focus on the binary classification problem. Okay, so now why not use what we have so far? So +1 and -1 are sort of the same things that the values as any other. So we perhaps could use a regression. You have, I don't know, you are asking, I'm willing to pay 100,000 euros for an apartment, right? So, and then you can go and you can have, so this may be so this will be apartment size. And this is just, I'm willing to buy this, I'm not willing to buy this for 100,000 euros. Okay? Am I willing to buy this? And perhaps the small apartment sizes you don't want for 100,000 euros. So there will be a couple of points, maybe somewhere here. Okay, this is -1, right? And then there is a +1, and some of them you would like to buy, right? As long as it's big enough, you probably would buy it for 100,000 euros. I mean, and here it's getting, I will buy it for 100,000 euros. I mean, this one is really, really nice. If somebody offers it to me for 100,000 euros, I have to buy it. Okay? So what's the problem running regression on this? Yeah?
It doesn't take into account how much you would like to buy it, for example?
This thing? No, it's a classification problem. So somebody offers me this apartment for 100,000 euros, and I say yes or no.
If you use this data for training, then for example, if apartment is really big, then probably it should have some more weight, and that's why this.
Why? I'm just, I just want to train the function, and I have a target value, right? Is he going to buy it for this price or not? Yeah?
So the obvious thing is that your predict value is different from just -1 and +1. You will sometimes predict 0.5 or 7 or something like that. So you are, strictly speaking, not generating correct outputs.
So one thing that I can actually do, I can, run on this data I can run a linear regression, right? So I will get a line which would look something like this, right? Which is even mildly relevant, because yes, you are saying, yeah, you get a value -0.2 or whatever. Okay, I will then take a sign. Okay, so it's negative. I will take, I will say -1 in the end. If it's positive, I will say +1 in the end. That's easily solved. But what's the problem with this thing? And it might be even mildly useful. Well, the problem is that, if you look at here, I mean, this is actually kind of okay. I mean, okay, if this is negative, it's probably better to be positive than negative here in this area, right? So error function is based on the difference of the target value is fine. Here, maybe. But what about here? I mean, this function tells you that strongly, yes, buy this apartment, and there will be like large error associated with that, right? Because you are too positive or too negative. So that's really bad for training, right? You don't really want to do that. So, and any function that is based on a difference between target value and this one is likely based on some kind of regression is likely to not be very good. So we need to somehow fix this. How can we fix this? Yeah?
We can use different functions.
We can use different set of functions. For example, sigmoid is a good function. So let's part problem with this classification thing is that you sometimes want to use -1, +1, sometimes want to use 0, 1. So now we switch to 0, 1, okay? So what's the sigmoid function? Sigmoid function looks something like this. So it's a function that is between 0 and 1, okay? And it looks something like this. So it never goes below 0, never goes above 1. And it has some kind of phase transition, so sort of quickly goes from 0 to 1 at some point. Okay? So this is sigmoid function. So this is called sigmoid function. And so we will be looking at the hypothesis space that basically we will still have parameters theta. And we will take the input feature vector. It will take the same thing, so it would do scalar. It would do a scalar linear combination based on parameters theta. But then what you would do, you would run it through this sigmoid function, which will get it back to the interval between 0 and 1. Okay, so this is the kind of functions that we will use. And the sigmoid function is something like this. It's 1 over 1 minus e to the minus c. So it's shifted, the 0 here is here. And here it's 1/2. 1. Yes?
For example, you can use also the jump function.
Okay.
The jump function, which is till 0, 0 and after 0, 1.
Okay, we will talk about this later. Not in this class. Not in this lecture. But we will talk about all kinds of variants later. Okay, so this solves part of our problem. We are not going to, with these functions, we are not going to be penalized for actually, being too positive. Like if you are too positive, you're still 1. That's good. Now you can also interpret it, kind of, okay, if you are really, really close to 0, then it's minus 1. If you are really, really close to 1, then it's plus 1. And if you are somewhere in the middle, well, it's it tells you some kind of confidence, maybe. Whether you are confident in your choice or not. I may want to buy this apartment, but I may not. Okay. So how we put this we need to put this uncertainty into our evaluation function, into our error function, right? Yeah?
The sequence function, correct?
I think so.
It should be 1 plus
It should be plus, right? Good, thanks. So we need to somehow figure out a good error function that will actually take this into account. So maybe the values between 0 and 1 are great for interpreting as probabilities. Okay? So let's say that I'm not outputting the sort of whether I buy it or not buy it, but that I'm going to output the probability of buying the apartment. So then what? So of course there must be a right answer, right? There is some, you buy this apartment, you don't buy this apartment. So how do I take this into account in the function? Well, if I treat it as a probability, so I can take all these training examples, right, and treat them as a probability. So if I have a h theta x y. If this was if this was 1, right? I want to buy it. Then I would like also the target value to be 1. So put this in here. Okay. And I will run it. Something like this. So let's say that the output, our function only gives me zeros and ones. Okay? Only gives me, and also yi's are zeros and ones. So now we have target values not -1 plus 1, but 0, 1. Okay? So that we are not confused. So if I had that, if I just got the values zeros and ones, buy or not buy, then if I bought the apartment, that is the value 1, and the value was 1, I would get what? Here I would get the reward 1, and here I would get again 1. Okay? Sorry?
It's kind of this problem, so section what is 0 are
1 to the 0 is 1.
what is 1 to the r.
Okay? So it's 1 to the, sorry. No, it's 1 to the 0, 1 to the 1 plus 0 to the 0. 0 to the 0 is 1. Anything to the 0 is 1. Okay? If it was the other way around, if I didn't buy the apartment and the value was, and the target value was do not buy the apartment, then I will get 1 here and 1 here. Okay? Get 0 to 0 and 1 to the 1. And if it was this other, the other way around, what would I get? So I get 0 to the 1, which is 0, and 0 to the, doesn't matter because this doesn't matter anymore. If it's something, 0 times something doesn't matter. So this is really like a strange function, right? Because this gives me, like for every training example, if I get it right, it gives me 1. If I get it wrong, it gives me 0. If I multiply this all, I would get 1. I would get 0 if I made even 1 mistake. But I have all these values in between, okay? So if I have values in between, then the closer I am to the target value, the better I am. So this is actually the problem. So what is this? Is actually probability of getting the right choice. Okay. Because I am taking this this one thing, the thing that is not correct here. So if I should buy the apartment, I'm multiplying by probability that I said I would buy the apartment. If I am not buying it, and this would be 1 because this would be 0. Okay, and if I don't buy the apartment, then this part would be 1. And this part would be probability of me saying not getting the apartment, because probability of me not getting apartment is 1 minus the probability of me getting the apartment. So this is really probability of getting right answer for training sample. Well, and if I want to do probability of getting complete everything right, then then I multiply all of these. So this is something called likelihood of the parameter set theta. And I don't like this a little bit because it has a multiplication. If you would like to optimize this, you would like to get this as high as possible, right? That would be your training. So you would really want something that to get you back to the. It's better to have sums than multiplications if you are going to use derivatives. So we will take maximizing L theta is the same thing as if I take logarithm of this, okay, and I also want to just get it back to the original error function thing. Error function should be high when you are. So I will minimize minus log. Okay. So maximizing this actually is the same as minimizing minus logarithm of this. Logarithm is a monotonous function, and if I take minus logarithm, then I will turn maximization into minimization. And so minus log this will be my j beta. So let's rewrite it. Our function, error function j theta will be minus sum of yi times logarithm of h theta I plus 1 minus 1i times logarithm 1 minus h. So I've just taken the logarithm of this, turned products into sums, turned multiplication, turned exponentiation into multiplication, that's it. So this was, we started with a new machine learning problem because before we have done regression, which was, you wanted to get a real valued target value from some real valued attributes. Now we want to get like prediction of classes from real value attributes. So now we want to just an answer, belongs to the class, doesn't belong to the class. So it was a 0-1 answer instead of a real valued answer. So this is a classification algorithm or classification system, in spite of the fact that it's called logistic regression. Okay, it's just meant to confuse you. So this is so we've started on classification, and so there are a couple of ideas. I mean, we have started with maybe we can use linear regression for this, but we have changed a couple of things. First thing that we have changed, instead of giving a value between -1 and or minus infinity till infinity, we just restricted the output values between zeros and 1, and most of the time the value will be very close to 0 or very close to 1. And the way how we have done it is that we have instead, we still are doing linear combination of attributes, and then we are putting the result through some kind of nonlinear function which is called sigmoid. So basically the set of the hypotheses for our system will be set of the hypotheses, the same set of parameters theta as before. And so these are the functions that turn vector x into, so basically take linear combination of the attributes, so that's it. But instead of just having a linear combination, we will pass it through through this sigmoid function. And the sigmoid function was, gz is equal 1/1 plus e to the minus z. So that's the first thing. So this function we have shown, we looked at it last time. It will basically gives you, most of the time it will gives you values or it will always gives you values between 0 and 1, and most of the time it will be very close to 0 or very close to 1. Okay, so that was one idea that we have done. The other idea that we have done was that we have changed the error function. So we will not be using the square of the difference here, but instead we will use a function that was motivated by some kind of probabilistic interpretation of this. I won't repeat how this is motivated by probabilistic interpretation. I will just write down the result that we had. So we had a function j theta is minus sum of yi times logarithm h theta xi plus 1 minus yi. Actually, this should be minus. No, that's okay. Times logarithm 1 minus h theta xi. So this was the function. And it was somehow related, we have computed some probability of getting the right answer if we chose, if we took this result from the classification as a suggestion of how often we should actually choose the positive or negative class, and then we just take a minus logarithm to get the, you know, to turn the products into sums, and that's it. And I think that's where we finished last time. So we had class of hypothesis, error function. What do we do next?
We need to minimize the last.
Yes, you want to minimize so we want to minimize this error function. So basically we get the training examples, and the thing that we want to do is we want to find the parameters theta that will minimize the error function on the in the training. The same thing always, okay? And so we want to minimize j theta. So find parameters theta that minimize j theta. And we said that what we will do is that it will be difficult to actually find a closed solution like it was before with linear regression. So instead we will use gradient descent as suggested in the previous classes. So we use gradient descent. And basically what we need to do is how the gradient descent works is we start with some parameters, and then we basically update the parameters based on the training set and based on the error that we see. So here we take and we do this iteratively until, you know, the parameters converge or until we reach some stopping criterion. So in this case, so we need to have a rule how to update the parameters in each step. And so this is the denotation for the parameters in I plus first step. Okay. So and they will be derived from parameters in the ith step as follows. We take the parameters and we basically okay, so we take basically gradient in the particular in the previous at the previous point with the parameters, and then basically update with this formula. And this is the same thing as we have done before. Alpha is again the learning rate parameter that is. This is the part of the black magic. So we want to find this, right? So to do that, we will do chain rule, because like this is a reasonably unpleasant function, right? So we need to do something, and that something will be I mean, you know how the chain rule works. So when we want to take derivative according to something, right? We take derivative according to something else. And then we do the derivative of that something else according to what we wanted. So the chain rule will be the hero of the day today, all the time. So we have this j theta, and first we take derivative according to this thing. Okay. So you imagine that this is your variable now, and you are doing derivatives based on this variable. So here, why this particular thing? Because you have it, you have this. It's somehow here, right? And it's also somehow here. Well, we will see there will be something related to that. Okay, and then we need to multiply it by taking this function over theta j. Okay, any questions so far? Sounds reasonable. Okay. So, what's next? So this is this first part, right? If you take derivative according to this, right? You have so you're taking derivative according to this variable. So what happens? This turns into minus y as the times 1 over h theta x, right? Does it? This looks weird, right? Okay, I'm doing something wrong. Please help me to figure this out instead of discussing this among yourselves. So what am I doing wrong?
Should be just because you divide by logarithms.
I think I think what I'm doing wrong is I have this. Now it's fine, right? So instead of I first am doing derivative according to h theta x. H theta x is my function, right? The one that my hypothesis. And then I'm doing derivative of hypothesis according to the value theta j. So that will make more sense. So now it actually works, right? Because now logarithm of h theta x, derivative of that is 1 over h theta x. So I get minus yi. Oh, and one thing, to simplify things, okay? I will just be working with one training example now. To simplify, work with one training example. So this is my training example, okay? So this what happens is this turns this sum into just just have one training example. So this will be y times logarithm, and this will be 1 minus y times logarithm. Okay? Why am I doing this? Well, there are two reasons. First of all, I mean, these sums really complicate things, and it doesn't really matter. I mean, you really, when you go through all of this, all of the derivation, and you want to do it for multiple training examples, you just, you just add all the updates right here. Another thing is that I think Vlado has told you in his lecture that it's actually usually it actually makes more sense to do stochastic gradient descent. And stochastic gradient descent works on one example basically. You are doing, selecting one random example and updating with that example. So this is why we are doing with a single example, single training example. Okay? And now I may be untangled from my tangles. Okay, so from this first part, from here, I get this. From the second part, I get this part. Okay? And now the only thing that I have to do is I just have to, take the derivative of the target function of the function over the function h theta x over theta j and multiply this part. Okay, and I can still work on this. Chain rule is a good thing. So because like this function h theta x is this has a logarithms and things like that in it, so it's actually reasonably complicated function. So I will actually split this again, use the chain rule to actually do this derivative. So instead of doing this directly, I will decompose it. So this thing is basically G of theta transpose X, right? So this is the scalar. This is the scalar multiplication. This is basically linear combination, and this is just application of sigmoid function. Okay. So I can do two things. I can do one thing. I can separately take the derivative of the sigmoid function and separately take the derivative of this inside. Okay. So again, using the chain rule, I will use d over this. Okay. And then times okay, I can still, now I can find, I can look at this. This is easy, right? Because this thing is, this theta transpose X is simply sum over, theta I xi, right? It's the same thing. And if I look at this and take a derivative, it's all parts will be zero derivatives except for the one that has actually theta j in it. Okay? So the only thing that will remain is what? Only x will remain, xj, right? So this thing will turn into xj in the end. So I have already resolved this part, okay? This is, nice formula, no derivatives in here. I have resolved this part, this is xj. The only thing that remains is derivative of the sigmoid function. So the only thing, one thing that I'm doing, that you might not have seen, I'm at least trying to be consistent. Sometimes I write delta for partial derivatives, and sometimes I write d for real derivatives. And the only difference is that when I'm writing d, there is only one variable involved. Okay. So for example, here I have written d because there is like some function g of something over this something, and this is only variable involved. There is no other variables, therefore it's a regular derivative, while this is partial derivative because there is multiple variables involved. Okay, this is why I'm writing sometimes d and sometimes delta, and it might actually be a bit confusing, and I might even make mistakes in this, not realizing that sometimes I should write this and sometimes I should write that. Okay. So now the only thing that remains is derivative of the sigmoid function. So we need to find the derivative of function gz over z. And so the function gz is basically 1 over 1 plus 3 to the z over z, right? And so again, we will use chain rule. The first thing that we will do, we will do okay. So we will do this as derivative 1 over x over x. So this is basically okay. Let me write it down. So first of all, we will do this derivative, okay, and then we use So this is again chain rule, plain and simple. So this is 1 over x, means that the result is 1 over x squared. Minus 1 over x squared. Okay, so this is minus 1 over 1 plus e to the z, right? Squared. And the second thing, so this is 0, right? And this is e to the minus z over z is just e to the is minus e to the minus z, I think. So this is minus and minus, this gives us plus, so the result is 1 over 1 plus e to the minus z squared times e to the minus z. So I just removed the minuses so as not to make it too confusing. And now we will do a little bit of tricks to rewrite this. So I will rewrite this as 1 to the 1 plus e minus z times e to the minus z over 1 plus e to the minus z. So what I have done, I have redistributed this square into the two terms, okay? And also I will do this trick that we are very happy to repeat again and again. So I will add one and subtract one. Okay, why not? So why am I doing this? Is because now if I put it in the parentheses as like this, I will get 1 over 1 plus e to the minus z times this is 1, right? Minus, and what will remain is 1 over 1 plus e to the minus z. So in fact what we are getting, I mean, this is just the original function, right? This is just the sigmoid function. So we are getting gz times 1 minus gz. So this is the derivative of the sigmoid function. Okay, and yeah? Where? So now let's go back to the beginning. So we have, let's put it together, okay? So we are interested in derivative of j theta over theta j, right? And so we know that this first part should be, I will rewrite it a little bit, but it's the same. So it's 1 minus y over 1 minus j theta transpose x. Right? I've just expanded h theta x, okay? That's the only thing that I've done here. Minus y over g transpose x. So it should be the same thing as this thing over there. Okay, I'm just put the, instead of h theta x, I put the whole thing in. Okay, then we have this derivative, right? So we need to put g times 1 minus g transpose x. And then the last thing that remains is xj, right? That's what we are putting in there. So that should be the derivative. Now let's simplify a little bit. Okay, so this is nice, right? Because I mean, I have this thing, and if I multiply this thing by this thing, it turns out that this thing here is the same thing as here. So when I multiply this, I get 1 minus y stays here, right? And then this will disappear, and I will just have G theta transpose X. And again, I will repeat the same trick for this part. So again, this thing and this thing is exactly the same, so it will disappear. So minus y times 1 minus G T transpose X times Xj. Okay, let's look at this again.
Everything is times xj.
Everything is times Xj. Ah. Yeah. Okay. So the problem with doing derivatives on the board, you might have found on some tutorials in your earlier years, is that you actually can't see what you are writing here because you're too close. You don't see the whole formula. That's the problem. Okay, now let's continue the fun, right? We can also do this this expansion here. So this will be like g theta x minus y times g theta x, and this will be minus y and minus y times g theta x. So y times g theta x and y times g theta x will cancel out. Okay, so y's are out. The only thing that stays is, so this will be 0, and the only thing that stays is g theta x minus y, this part after the expansion, and this is time x. So what is this? This is simply value of our function, right? So this is h theta x. So this is actually nice, because what we are saying is that, this is some kind of expression of the error. So where we are, what's the difference between y and value of h theta x, and we just multiply it for whatever reason. We are multiplying it by xj. And this is, that's it, right? This is our update. So our update rule for the gradient this time will be very nice actually. So update rule is theta I plus 1 is equal theta I minus alpha times h theta x minus y times x. Okay, this is all of these, we have completed all the individual parts of the update vector, and now you put it together, it's simply, this is a constant, this is some kind of constant, and this is the whole vector, basically, for all of the individual parts. So this is a really nice update rule, that's why we are doing it. I mean, we went through. If the result of the complicated computation would be, some complicated, horrible formula, I wouldn't do it here. But this is really, ends up really simple. And you might, somebody might actually try to sell this to you as, we just do, this is some kind of error, and we are trying to distribute it in a way that is related to how the individual parts of the vector, something like that. But it's, the real justification is simple derivative. So don't believe people who are trying to find too many analogies in this, even though it's really trying to give you analogies. It's suggesting analogies, but they are not there. Okay, because then you stop. I mean, once you start accepting these analogies, you stop understanding why this actually works. Okay, so now we know how to do logistic regression. Any questions? Yeah.
Stále nejaký problém, ako vznikajú pri regresii, ako lineariza alebo
So actually, so the question is whether there is some numerical problems that are similar to those that we have together with regression. And the answer is very simple. Once you take the regression, once you do the regression, once you switch to the numerical methods, you usually don't have these numerical problems that come from solving multiple linear equations with unknowns, right? So most of the times when you ask about this with respect to linear regression, they will tell you just switch to the gradient descent. And now we switch to the gradient descent by default at the beginning. So now we started so logistic regression is again really simple method. So the question is whether we have anything more complicated for classification. And the answer is, of course, yes, we do. So we are now ready to turn into like the most hyped model that exists at the moment, and it's neural networks, okay? And we will not be covering neural networks in very much detail, because there is a whole class dedicated to neural networks. So we will just do like a simple example, and that will be it. And you will also see more on the tutorials of neural networks. So the neural networks, basically the idea from the neural networks is that since we have, I mean, this logistic regression, you can imagine this as a very simple unit, right? So you can imagine it as, having something that takes as inputs several values of the attributes, right? And then outputs some value of the attribute. And this value is between 0 and 1 here. And basically what happens here is that first these are combined by linear combination, and then they are passed through some nonlinear function. And the question is, what happens if we connect multiple of these together? Okay? Because, I mean, you can, right? So we can do something like this. We can have like, these are the original attributes. So x1, x2, x3 up to xn, right? And then we can have not one of these, but maybe several of these. So we have, so this is input layer. This will be called hidden layer. And it will have basically P, like for various reasons we call these neurons. So it will have P neurons. Each of these neurons now will have like all connections from all attributes. Okay? And then we combine these again into one, and this is called output layer. We want one target variable, so we just have one neuron here. So we have our output layer, and it will give us some value. So the first question from me, what are the parameters of this network? I mean, here we just had, some parameter vector theta with like as many parameters as there is number of input attributes. So what are the parameters here?
Weights on the edges between the individual logistic regressions.
Yes, so for each of these neurons, we have to have like all of these, because this is a linear combination of the inputs. So we have to have somehow weights for the linear combination. Okay. So for ith neuron, okay, in the hidden layer. Neuron in hidden layer. Okay, we will have something like, you know, let's denote this UI1, UI2, UIN. Okay, there are n inputs. So this is basically linear combination and plus nonlinear. And the function that we will be using here, we will be using the same sigmoid function here, but in general it's called activation function. Okay? Activation function. And we will use sigmoids here. But, you know, actually sigmoid is not the best thing to use. But
Sorry, where the weights came from? Because we don't have any weights in what.
oh, we do. Theta 1, theta 2,
Okay.
theta n, right?
Yeah.
So there are weights there, so there are also weights here. And also there must be, so each of these neurons in the hidden layer, they have like n weights associated with them. And also this output, right, neuron has to have some weights. So output looks something like, you know, and we have, but here we have not n inputs, but the size of this hidden layer. So there will be parameters theta 1, theta 2, until theta p. Okay? So we can write these parameters down in a more compact form. So there is a matrix that we will call U. And this is basically all these weights over there. So U11, U12, U1. And so these are the weights associated with the first hidden neuron, U21, U22, U2. And these are weights associated with the second one, and so on until UP1, UP2, UPN. Okay? And so this is one parameter. The second parameter is vector theta, and this is basically theta 1, theta 2.
In the matrix U, we have weights for every single layer.
If you have multiple layers, then you will have to have weights for every single layer.
Oh.
Okay, so this is really simple example. I mean, there is no reason why we cannot, and actually, like deep learning actually does have lots of these layers in here, with even different types of activation functions, different types of connections between the layers, things like that. So, but here we are just using these very simple examples where we just have one hidden layer, and we have one output neuron, and that's it, and we have input. So what's our, again, the same thing as before. To build our learning system, we need to sort of specify what's our set of hypotheses. What's our set of hypotheses? Well, this can be easily written as a function, right? So it's simply a set of hypotheses, a set of function. Now we have two sets of parameters, theta and u, right? And basically it turns input vector x into, well, what happens in the first layer? Well, we take the matrix U and we multiply it by vector x. That gives us a vector of all of these linear combinations in each of these neurons, right? Now we take and all of these values we pass through function g. So we get, again, so this is vector of p values. we pass it through the activation function. We again get a vector of p-values. And now what? Now we are just doing theta transposed, right? This is vector. We have column vectors. So we apply theta transform in here. So we get a linear combination, and again we pass it through function g. And that's it. So a little bit more complicated than before, but it's the same idea. And we also need the error function, right? So this is hypothesis set. And we also need error function. And here, I mean, we could actually go and use the, for example, the function from our logistic regression, but we won't in this particular example. So we will use the regular squared, square of sum of squares of differences. So our function j theta u will be simply 1 over t sum over all training examples h theta u xi minus yi squared. So we are turning all of this, we are turning again into the same thing as before, same idea. So what would be the next idea? What we ought to do to build a training algorithm? Sorry?
Minimize it?
Well, we want to so we want to minimize this function, but how we will do that? By gradient descent, right? So minimize j theta u using gradient descent and again, because we don't want to spend like A, stochastic gradient descent is actually better, and B, we don't want to write lots of sums. In the rest of this lecture, we will assume there is one training example, xy. So all the sum doesn't really matter here. Okay? For simplicity, one training example. And so we want to do basically, do the same thing. We want to start with some parameters, compute the gradient, multiply it by alpha, which is the learning speed, and then we want to subtract this from the previous values. That's the plan. Yeah.
You have a deeper network than all the hidden layers in CP neurons, or does it?
Actually, no. I mean, you can. So here I have turned, I have the layer of size n, and then I have a layer of size p. So basically, what I've done, I have turned the n values into p values by p neurons. There is no reason why I can't have like different sizes on different levels. So basically, my matrices that will correspond to the size of the parameters will be corresponding. If I have like some P2, then I will have a matrix that will have P1 times P2 value, P1 times P2.
So we will have multiple matrices for...
Yeah, for each layer there will be a separate matrix.
Oh.
And you will learn all of this, if you take neural networks, you will learn all of this on your own. Or not on your own, in that lecture. Or on your own, I mean, it's what we are doing here is the basic thing that the most basic example, but all the other things are really a straightforward generalization from that example. Plus there is, the reason why we are doing these computations is to understand what happens inside all these libraries that actually work with neural networks. But in fact, what happens, like in reality, you never actually program this. Because you have like nice libraries that will just, you specify this layer, this layer, connect it in this way, and now use this error function at the end, and now optimize, right? And that's your function. And you do some magic, which is basically very, very related to what we are doing here, but avoiding all the numerical problems and everything, because like lots of people spend lots of time on writing this, and you'll come up with the solution. And you don't need to worry about that. But we want to know, but that's the, that looks like a black magic, but it's not, because what we are doing here, we are showing you at least an example how it works. Any other questions? Okay, so we have some hard work ahead of us, but before we do that, I want to mention one thing. I mean, the question is, this looks like a pretty simple idea. Like, if I have some classifier that seems to work well, perhaps connecting multiple of these classifiers together in some nice way might give you even like a nicer classifier, right? So my question is why we didn't do this for linear regression? So you can imagine, right, example, let's put this. So remember, you can use linear regression even though it's not generally advisable. You can use linear regression for classification, right? So let's do this. So let's have an example where we sort of have two input variables, two attributes, x1, x2, and also intercept term. And now we want to use, linear regression to do the classification. So basically, whatever comes up above 0 is positive, whatever comes below 0 is negative. So basically, what would happen if you use linear regression, you could visualize it, right? So this is x1, this is x2. I mean, linear regression gives you linear combination of these. So you would get some kind of line in here. And on one side of the line, there would be plus, and on the other side of the line, there would be minus. Okay, so the classification would say, okay, let's take this part of this plane, and this is our answer, right? So that's linear regression. So let's say, why not take and why not combine, in a similar way. I can take, I can even draw it in a similar way. So I have x1, x2, and intercept term 1. Intercept term is really important. So you should be sure that it's in there. Sometimes it's there by default, sometimes not. So you should really look whether intercept term is there, because otherwise you would constrain yourself to things that go fully 0, which is not good. Okay, so intercept term, let's say we take and you can have like two hidden regressions, right, in the middle. So something like this. This is just a linear combination of these three things from the beginning, and then another linear regression here, and you would have an output. So what's the problem with this model?
Well, all the linear regressions are as linear functions, so you're basically like summing or combining linear functions, which gives you linear function in the results.
Exactly. So that's the problem with linear regression. Since I don't have this, passing through the non-linear activation function, what happens here is I simply, sum of the two linear combinations is just a linear combination. So I just get one simple linear combination. This doesn't add anything. This doesn't give me anything new. I already have this particular function. I already have in my hypothesis set. So whatever happens, I will never be able to, do anything more complicated than subplanes on this plane. Then like one side of the line or the other side of the line. That's it. So what happens when you have, instead of here you combine, perhaps the same for the logistic regression, right? Perhaps if I combine it in this way, I also get the logistic regression. I mean, if you take the logistic regression, right? It's still, you take the plane, you take the line, the plane, okay? And then, again, it passes it through some nonlinear function, but again, on one side there will be plus values, on the other side there will be minus values. So it doesn't seem that there is anything smart that I'm doing with neural networks now by combining these together. Well, not necessarily true, because what I get, so let's say I take two of these, okay? I take this one, so what I get here, like I get here like values, here will be maybe plus one values on this side, and here there will be zeros, right? If you are far enough from the line, around the line there will be some fuzzy area where there are other values. But if I am far enough from the line, I get plus one and zeros, nothing else, or almost plus one and almost zeros. So what happens if I add second plane like that? I add something like this. So, and let's say I have plus ones here, right? And zeros in here. So then in the middle, I get what? If I sum these together, what I get? I get, in the middle, I get what? In this area, what do I get? Well, I get plus 2's, right? In this area, minus some, area close to the line, which I don't care about at the moment. Here I get plus ones, right? Because plus ones from the red part, and here also I get plus ones. These are from this white line. So suddenly I can do, this, right? This I cannot do with linear function easily. I can just do this part of the plane. If I add the third neuron, I can get like a more complicated areas. So this is what actually the nonlinearity brings us. By putting together more nonlinear function, we actually get new things. We don't get the same thing again. Okay, you cannot do this with one logistic regression, but you can do it by combination of two and one output neuron. Okay, so this is why neural networks are in general more a stronger model than just a simple logistic regression. Any questions about this? Okay, so now we are ready to have some fun. We need to go and take derivatives, right? So we want to use gradient descent. So basically we want to take some parameters ui, ith version of parameters u and theta, and we want to update them with alpha times gradient over u and theta with ith from ith version of these parameters. J, I think I just switched u and theta doesn't really matter. And so these are new parameters. U I plus 1 So this is our gradient descent that we want to do. Okay, so the first thing so there are two different types of derivatives here. There are derivatives based on values u and derivatives based on parameters theta, right? So we will do first the theta ones because they are simple. So let's see what happens. And we are doing it for a simple example. So we are doing derivative j u theta over theta I. Okay, so what are we going to do? Well, this seems pretty complicated, right? There is like this complicated thing somehow. It needs to be, we need to do derivatives over something that is like really bad. So we need to simplify this with, the right weapons are good notation and also chain rule as before. So good notation. So let's see. Let's write it down. So what happens with respect to this this final neuron, right? This is output neuron. So we have a layer of p neurons here. And each of them, I mean, it has, something comes through the linear combination, and then finally it gives us some output value, and I will mark this output value as Z1, Z2, etc., and ZB. Okay? And then these values of Z are combined with these theta parameters, so I have parameters theta1, theta2, theta p, and they are combined into one single value. So this is value, I will denote it A. Okay, so this is value that is just a linear combination of these z's, these thetas. And then I will pass this theta through the nonlinear function g. Okay, so I get ga here, and that will be my output, and I will also denote this as y hat. Okay, so this will be my notation for this layer, for this output layer. There will be other notation for the other parts of the network. But right now I'm just interested in this. So what I am really doing is I'm computing the derivative of y hat minus y. So y is the target value, right, of our one training example. Y hat is the estimate that something that comes through the network, that is estimated from the network. And I am doing this thing, and I want the derivative of this. This will be. And so what's the good value? Well, I'm going to use chain rule. So I'm going to switch variables until I will get this at the end, right? So the first variable I will switch over this is let's take derivative over this. So the next thing I have to take a derivative of y hat. Now this y hat is simply GA, okay? So what's the easier way than taking, derivative with respect to A? I'm continuing now, so I have to put the A here. This will be partial derivative. And this A is what? It's sum of theta I zi, right? So it will be easy to take derivative over theta I. So I decompose this complex derivative into like 3 different derivatives that are perhaps a little bit simpler. Well, they are simpler. This is very easy, right? This is simply 2 times y hat over minus y. This thing is, I don't know, well, I have done a derivative of sigmoid function, but there can be other activation functions, so I will just keep it as g derivative of A. Okay? And then I will multiply this by this derivative, but this derivative is really simple because it's just the sum of this theta I zi, right? So all of those derivative, all of those partial sums are zero except for the one that actually involves theta I. And the result is here zi. Okay. That looks simple enough. Let's see what happens with the second layer. So again, I need to do the derivative of j u theta over one parameter uij, right? So, what do I do? Well, again, I need some notation. So, taking over from this picture, I have, so this is so there are now 3 layers involved. So one is, x1, x2, xn, right? And then there is output layer, so there is A, and there is this GA here, which is Y hat. And then I have this middle neuron, so I have these things. So there is UI1, UI2, UIN, okay? And there is also, there is multiple things here. And there is, so once I do combination of x1 times u1, x times u, and so on, I get a value, let's say AI. Okay? So that's ith neuron, okay? And why I'm doing ith neuron? Because the value that I'm interested in is actually related to ith neuron. And okay, and there is zi. That's actually taken from the previous picture. Okay, so this is simply AI passed through the nonlinear function through G. Okay. So now let's do chain rule again, because we are happy using chain rules. So first thing that I have is I have to take derivative of, it was a success, so let's do it again, according to dy hat. Good, so dy hat again, this is simply g of A, right? So we do derivative according to A. Okay, now we do, again, we have A, and we need to do derivative according to what? Now. Well, before we did derivative according to theta, but that wouldn't help us. Because now that would be dead end, right? Because, theta doesn't have anything to do with so I need to do derivative according to the I value now. Okay, so now I am here. So what next? I need to do derivative of zi. I need to get back to this part. I need to go further. So I need to do derivative of zi over ai, right? And the next I'm almost there. I need to do partial derivative of AI according to uij. And I'm there. So it looks like a rather long chain rule, but it's at least simple. I mean, each of these terms are actually simple, right? Well, this one is simple, we have done that before. So this is 2 times y hat minus y. This one is simple, we have done, yep.
Why is there equals?
Sorry?
Is it equals should be like multiplication.
This should be multiplication. Thank you. So now I need to, this is just g derivative of a, right, times, okay, so what's this? So this is again, this is sum of theta I, zi. Again, all of the values are, all of the parts are 0 except for the one involving zi. And the result will be theta I, right? Yeah?
Can you change the normal derivatives with the partial ones?
Yes. There are some exceptions to this, and there are lots of things that we are hiding a little bit. So it's a little bit more complicated, not that much. I mean, everything that I'm doing is technically correct, but if you try to apply it in this way in some strange situation, you might actually get into problems. But you would have to take like multivariate analysis to actually do this properly. We are trying to understand. We are not trying to do new things that nobody has done before. Okay, let's go further. So now I have this zi. Zi according to AI. Zi is simply g ai, right? So it's again g derivative AI. And we are almost at the end, so AI is what? It's a linear combination, so it's uij times xj, right? So this sum, again, the same trick. Everything is 0 except for one term that involves uij, and that term has xj here. Yeah, looks like what I have on in my notes. Yeah, any questions?
Tam asi v tom úplně výsledku, tam máme dvakrát y dostriedkou minulý y, ale mi to mi iba, že dvakrát y dostriedkou, iba bez toho ďalšieho minulý y?
No, because this is actually also a chain rule, right? So you first do derivative of this over y hat minus y, which gives you 2y hat minus y, times the derivative of inside over y, which gives you 1. So I have hidden one chain rule in there. Okay, any other questions? It's really simple. More or less, with the right notation and with the... Okay, so what did we get? So basically what we are doing when we are training neural networks, right? Let me get rid of this. So when we want to train a neural network, so training neural network with backpropagation, training neural network with gradient descent. So basically, first you start initializing some, u0 and theta 0, so the zeroth version of the parameters. Good question is how. There are lots of black magic tricks that will help you to do that, and you will learn them in neural networks class. But you can try, random values. You shouldn't try symmetric values, so not necessarily. You shouldn't try setting them to the same thing, and don't set them to zeros at the beginning. Doesn't work really well. So I would say, for the first try, you can just initialize them randomly or something. And so now we iterate until, we are happy, until convergence, or until the values are, until the changes in the values are small, or until the error doesn't improve much, things like that. So compute y hat with current parameters. And as you can see, we are using a lot of the things that we compute in the middle, okay, also in this formula. So also keep intermediate computations. And so now, propagate back through the network. Basically, you update here, you update thetas as follows. Okay, let's put the k here, k plus 1, k minus alpha times, minus 2 times alpha, y hat minus y, g derivative a times z I, and uij you can update with the previous uij and add minus to alpha y hat minus y times g derivative a times theta I times g derivative ai times xj. And that's it. And this is, if you have ever worked with neural networks, you know that this algorithm is actually known as backpropagation algorithm. Again, there are lots of, there is so backpropagation algorithm is nothing else than gradient descent on the error function. There is no other magic involved. Anyway, so there are some, you can also make up stories because, this is the difference. Like this is error, and it's somehow distributed through the network based on the sizes of these, or the current sizes of the parameters. So you can try to say, I'm distributing most of the error towards the paths that are sort of affecting the network, the particular neuron most, or things like that. These are just analogies. There is no technical part in this. I mean, they are helpful mnemonic helping, but there is no, as far as I can tell, there is no specific idea in this.
I have two questions. One is, what are the I would say, variables in this model. We can choose the number of neurons, we can choose the number of layers, and error function.
Okay, so what do you have? So there are two types of variables or parameters. One set is called hyperparameters and one are parameters. Hyperparameters are those that you are setting as a person. Parameters are those that are learned automatically. So hyperparameters are, for example, number of hidden layers, number of neurons in each layers, how neurons in each layer are connected. For example, there is a good example. There is a good use for sparse connections. They just use like some random subset of possible connections, things like that. There is also activation functions that you are using. You can even use different activation functions in different layers. Then you would have to. You see that it's good. It should be nice. It would be nice if they were differentiable, if you can take derivatives of them, but it's not always true. I mean, people also taking, they say, okay, if in 1 or 2 points you can't take derivative, it won't be too, it won't be too bad, and we will do something there. So these are hyperparameters. You also, one thing that you have control over is also, encoding of your input. You can put the attributes in various formats in the network. Early deep learning was trying to suggest that whatever representation you take your input in, you just add more hidden layers, and it gets eventually turned into the right representation. You use right training algorithms. If everything works fine, well, most of the time everything doesn't work fine. So actually, it still makes sense to think about what's the most useful representation for the neural network, even though early deep learning studies tended to suggest otherwise. So these are hyperparameters that you can choose. And then the rest of the parameters, so these are these linear, all of these weights in linear combinations, they are learned automatically by, for example, backpropagation. So again, there is since we know how this works and we know that there are gazillions of ways how to do this gradient descent, stochastic backpropagation and things like that. We won't talk about it because you can, these are simple modifications that you can do yourself. And this is all we will learn in neural networks in this class. We will go to and work on other models from the next lecture. But I wanted to include this small lecture on neural networks so that we have at least a little bit complete overview of what's happening in the field. But there is a whole other class about neural networks that you can take. And we will have one tutorial on neural networks that will be playing these things like with hyperparameters.